Hello everyone, and welcome to our XP Solutions XP Live webinar, integrating 1D with 2D urban drainage models. So I've got with me here Gavin Fields, our resident XP Solutions expert. He's recently started out by himself as an independent consultant, but loves us so much he's come back to assist us with this webinar. No one better that you could be asking questions to. So this is probably a good thing that we're doing a 1D, 2D integrated webinar today. It's probably the key advantage that XP has over anything else in the market today is linking our 1D engine with the 2D power of industry standard engines. So we have a range of software products at XP, primarily focused on stormwater and flood modelling. And we integrate all of these capabilities in the one package, so it's nice and easy to just do your hydrology 1D or 2D, all in the one package, whilst bringing in your data from your existing workflows and processes from 12D, Civil CAD, and then getting your nice easy reports just to take out and putting your reports to council or to whoever you're doing your analysis for. So that's enough about us. I think we'll jump into what we're doing today.
Yeah, thanks, Ben. Glad to be here today. It's a very popular topic, integrating 1D urban drainage models, pit and pipe type designs, or river models, and integrating those with connected 2D models to give those visual representations that certainly clients and authorities are very keen to see in their assessment and reporting procedures. Just a quick overview of integrated 1D 2D models, tying in with the most recent webinar prior to this one from XP, which was a really focused 2D webinar by and Chris Huxley from BMT WBM was great to have along in that particular presentation. I'm going to try and call back to bits and pieces from that particular webinar and take the next step of getting those 1D elements into the models. I definitely want to go through some little bit of theory, not too detailed, but we'll show my favourite St. Venant equations, which is a core element to 1D and 2D models, to be honest. What to avoid, and really I'll probably go through the what to avoid in a demonstration. So I want to be a bit practical with today's presentation, not just bore people with a simple PowerPoint slideshow. We will get very interactive in today's particular webinar. So moving right along, and towards the end, of course, Q&A. So really straight into it. So for 1D, 2D models, going on from Chris Huxley's presentation not that long ago, he did go through and described relationships with 1D and 2D connections. And this particular screenshot shows a relationship between connections between either culverts and manholes or natural channels into 2D domains. And the key elements that we have to deal with, as described here, are elements relating to top of bank, relationships with the 2D domain itself, i.e. the grid elevations, be that at the surface for a gully inlet or a field inlet, so therefore top of the structure, or alternatively the invert of a river system, if that were to be connected directly to the 2D domain. And it's those river connections that I certainly want to focus on in my demonstration today, because it is a point of concern and something that we've seen over certainly the last few years. A number of clients at times have made what are effectively simple mistakes with the relationship of connecting these 1D elements into their 2D domains. They very rapidly identify that they've got a problem in their model, and they often land in XP's court to go, okay, can we please help out and try and resolve things? And of course, that's what XP is renowned for, in being able to help people with their models. But it's these simple connections that can cause problems. So I really want to focus on that today. Again, typical diagram. I'm sure if people have watched webinars before, you would have seen this diagram. It's been floating around for a while, but it's just one that we can't spend enough time on, to be honest. And in this particular screen, we're effectively showing an inactive zone which is being overlaid over a river system. Within that inactive zone, we have these nodes and links, as referred to in the screenshot. Node 159 and 158. Between those two nodes, we do have a 1D river section. To the left and right of those sections, we have 1D, 2D interface lines, and they're connected. They're the blue polylines that form the boundary along the inactive polygon. And then we have 1D, 2D connection lines, and they're represented as those sort of pink or magenta lines. And water can flow from either the 1D out across the connection lines and distribute along the 1D, 2D interface line, or alternatively come from the 2D and enter into the 1D. It's very important when we do run these procedures that, of course, we don't duplicate volumes. It's a very, very important component of stormwater drainage. We don't add additional volume to your model. It's not representative in the real world. If you start, unfortunately, not including inactive areas over these zones, you are potentially duplicating storage. And if you had detention requirements on your project, you could be misconstruing what you need, and that would certainly be a negative. And if you were to submit that to an authority for assessment, no doubt they would pick that up, and they would be asking you to update your work. So be very careful with volume in your model. But I'll move on. I don't want to spend too much time on these elements. The 1D components, of course, the general components inside the XP environment involve all typical structures, pipes, river systems, but can also include elements like pumps, weirs, orifice plates, very, very clever proprietary devices such as hydraulic brakes, etc. And nesting these or coupling these with two-dimensional models does take your 2D model really to the next level. And I'll move on from this slide. Again, river systems. I brought this one in just to highlight again it's the same screen from 2 slides ago, but just showing why we would consider taking that river from the bottom left of this particular screen, sort of clearly identifying that as the flows within this river are bounded by the defined banks, it is a distinctly 1D area of your model. We can also see on the bottom right-hand side the issues that are associated with grid-based relationships. And Chris in the previous webinar did talk about domain-related issues, so trying to have an appropriate resolution to your grid, and that might help avoid the issue that's shown here, where you just simply continually pull your grid size down until you get an appropriate representation of your channel. But often it's not necessarily an appropriate approach. So having them in 1D is a benefit. Chris, also, I've literally grabbed these from the previous webinar. Talked about boundaries, and I'm going to go into some alternative methods of boundaries. These are certainly appropriate in a purely 2D model, but at times they can actually be a little bit difficult to get information from. And in fact, by themselves, they provide almost no information. But what we can do is apply some additional connections into 1D objects, and they can really be very useful for reporting in your work, be they head or head flow relationships. So just going through, that's where those layers are applied inside the interface. Is under the 2D model layer, and we can add head or flow boundaries, head boundaries by themselves, or flow boundaries, etc. As Chris showed last time, we can apply those head flow boundaries with slopes, etc., or input flow points. For upstreams, a similar method. In Chris's presentation, he talked about having a pure flow boundary, pardon me, to the south and west of that particular model in that river system, which meant that the hydrology of that particular activity had to be undertaken externally to produce the graph. Whereas you may wish to include the hydrology. Again, a big part of the power of XP is that that integrated hydrology coupled to the hydraulic aspects. So using the runoff mode inside the software can really help you out. So again, just sort of scrolling through where those points are shows where that flow boundary is for this particular model. And we can see that's the hydrograph that would have had to have been calculated or copied into this particular 2D entity, which is a pure 2D entity, rather than being calculated as a 1D object. Internal flows can be located across the model, and again, so this is what's referred to as a direct rainfall connection. And I'm going to take this away and again go to some point hydrology in the demonstration shortly. I also talked about initial water levels, and these can be applied either globally or as polygons. So again, on the initial water level layer, we could nominate an area where we may wish to have an initial water level. In my personal experience, I've worked on simple projects like golf courses, and golf courses across their own site will have differing water elevations for the traps. I've donated a few golf balls over my years, but having the water elevations at different points across a site can be very important. Again, getting back to my earlier comment about volume, really trying to ensure you have the appropriate volumes inside your model as the initial premise to your model, and of course the conclusion to your model. And so the global values are under the configuration job control 2D model settings, and they're nominated under the levels tab on the left-hand side, and you can type in a value as required. Just a bit of a finale for the theory, and we'll jump into a demonstration after this. This is the scary part of what we do. I'm sure we all, as engineers and technical people, designers, love looking at these styles of equations, and having this wrapped into your interface really ensures you're taking into account the full complexity of the characteristics of flow in a dynamic state. So the semantic equations, otherwise known as the dynamic wave equations, if you're after a little bit more technical information on those, again, we could refer back to some of our earlier webinars. Hydraulics 101, for example, talked a fair bit on the dynamic wave equations. So again, by all means, go and sit in and listen back to those webinars off the XP's website. And again, taking into account these extra parameters, this is just highlighted in this particular component for both the 2D and 1D, is a difference between XP's flagship programs like XP Storm and XP Swim versus some of the other products that are often used by designers in the market. I might skip over this one and get into the demonstration, but this is again from Chris's presentation recently. How this culvert, which was a culvert applied across a driveway or a roadway access, providing that connectivity between two sections of a river. These were, in this particular demonstration, simply linked to the 2D at the pinpoint of the nodes. And that does at times come with complications, and I'll show you the pitfalls in our demonstration in a moment. But key parameters we do need to apply in our nodes inside our interface relate to elevations, critical information, of course. Some of that information can be extracted from the terrain, and we have on this screen RL 44.5, which is our invert at this particular location. We also have this at times arbitrary but quite important spill crest. And in the software, in the demonstration model I have in a moment, I will actually talk more about the spill crest and how it is talking to the 2D. This is then controlled by the node ponding options in the middle of the screen, and in this particular instance, the nodes are linked invert to 2D, and this is the start point of my demonstration. So we have a choice of either linking the spill crest or the invert to 2D, and hopefully it sounds it's relatively obvious that head walls and river systems or open channel type environments link invert to 2D, where closed systems like field pits or structures that connect to the surface at their top of their element, they link spill crest to 2D. Having those two choices there back to front can have impacts on your model and is definitely something to look out for. Just moving through those, sorry, I should have been clicking that. But I'm going to jump out of my little PowerPoint and go to a couple of models that we have set up. So in the previous demonstration, this was the sample model that was showing, very simple rural site. For demonstration purposes, this site is then converted to an urban area. So the existing model only had a couple of culverts across these waterways, and if I just zoom in on these, particularly this upstream one, just as a demonstration, we can see I have this culvert that's nominated across, and if I double click into this upstream node, we can see that RL44.6, we have our link structures here to the 2D via the invert. But one thing I always check on a model like this is to understand the physical characteristics of this 1D element and its relationship to the 2D domain. So to do that, I'm going to double click into this link, and I can see that fortunately I don't have any conduit factors on in this particular model, and if I did, I'd be looking for something like how many barrels that I actually have in play. So for example, if this particular model had 3 barrels in play, we would then have to go and look at what the size of those barrels were. This is a rectangular crossing, rectangular culvert, and it's 3.2 meters wide, and it's that width parameter that I have to really keep my eyes on. So if I have 3, I'm now over 9 meters in physical width inside this model, and if that were the case, I'd then go and check my my domain or the grid extent itself. I can right click on this layer, go to the properties, and if I go to the properties, I can see that my grid step size is 4 meters. So now by having a 9 meter wide element, I'd really have to try and talk from this node to more than one cell. At 3.2 meters wide, where we were when we started a moment ago, having the node just connect to the cell that it touches was okay, because it was less than the capacity of a single element. And if I turn on the grid underneath, I can see those relationships. And if I zoom right on in, it's probably a bit coarse with the aerial photo, but we would have to try and get this node in what I've just adjusted. Now that it's 9 meters wide, I have to get it to talk to more than one cell.
What would happen if you didn't do that? You underestimated that.
Well, effectively, you'd be putting a straw either at the inlet or the outlet of this particular system. And it's that constriction that you'd be effectively applying. You know, you don't want to have a device that's 9 meters wide going through a cell that's only 4 meters wide effectively. It's not quite like a straw because the characteristics of the node itself and versus the cell does have quite a lot of volume. So 4 by 4 square meters, you've got 16 square meters by the depth. The volumes do kind of help out.
Yeah.
Becomes definitely very important when you go to smaller or finer resolution models. So if you had a 1 meter model, you definitely want to really play around or go to what this next step is, which is having interface lines and connections to rectify the situation.
Okay, so you use an interface line to beat that issue with cell sizes being different to where the node hits. So wherever it hits, the software can just say it's inside that cell. That'll
correct. Absolutely right. So if we move on to the developed version of this site, and I might just turn a few of these layers off just to be a bit more clear in the site, but we quite clearly see we've got urban development. It is fake, so don't stress that we're going to flood everyone out, but it does serve its purpose. We can see we still have the river through here, but we do have some internal connections with some pipe work in and across the model itself. And to sort of further my discussion at the southern end of the site, this particular model, we try to solve the drainage issues inside the catchment with a detention basin. And I want to talk about the pitfalls there with 2D detention basins, and why 1D solutions are often more efficient. So if I zoom in at the upper extent of this particular model, we can see that we have our river system in play. Just to clarify this, I might turn off this background image. just looking at the contours, we understand where we are. But so on this particular link, I have a natural channel. If we have a quick look, we can view the section, respectively simple cross section to this particular channel, but that's okay. It is connected to the 2D via the nodes at the upstream and downstream extents. And here we have one of those pitfalls. And so in this particular example, I've done this on purpose, so don't stress. The spill crests have unfortunately been linked to the 2D instead of the inverts. And that's something that we do need to be careful with. This particular model, this river, should be linked invert to 2D. If we did leave it at spill crest linked to the 2D, it means that this top elevation is the connection point, and the water elevations inside the model would have to exceed that point before they really start getting into the links themselves. So that's certainly a trap and something that we have to be aware of. So very important here that we get this ponding option set correctly inside the software. The next step is to have a look at a couple of extra layers that we have under the 2D model to help us communicate between the 1D and the 2D. To do that, we start with an inactive area. And so this inactive area has been applied over the river region itself that's being represented by the 1D entity. The next layer is our 1D, 2D interfaces layer. And just for clarity, we've made that red. By default, software, it's actually blue. So don't go looking for a red layer. It will be a blue layer by default, but just for display purposes, it's easy to see red. And we've created a couple of lines that trace the left and right bank. You do also have the option of actually wrapping that particular line all the way around the perimeter of this polygon. So it doesn't have to be along the left or right, but just for today, that's where we've gone. The next layer on the 2D model, the layer control, is the 1D, 2D connections. And they're these magenta lines. And for clarity, I'm just going to turn off the inactive polygon, but just by turning it off, it is still there, of course. And if I just zoom a little bit closer, I can see that I have these magenta connections at each of the respective points where I want the water to communicate from the 1D entities under head into or out of the 2D domain. And we have these connections located wherever we have river components, but we also have fundamentally hidden connections at the nodes themselves where they're a gully pit. So if we realise that this is inside the street system, this particular node that I've selected, if I double click on it, this one has been correctly linked spill crest to 2D, and we then have the option to have the 2D inflow capture. And the 2D inflow capture is another a very important connection process for flows from the surface into or out of our 1D and 2D models. And the scheme is a respectively simple arrangement. It's a simplified version of the orifice equation. And get in touch with Ben afterwards, and he's able to provide a very simple spreadsheet that gives some comparisons between what the modification to this particular parameter is relative to some pretty basic or standard field inlet charts. So get in touch with Ben or the guys through that APAC education email, and that spreadsheet can be provided to anyone listening from today's.
What values here? Is that just the default we put in?
Yeah. This default value is a bit of a funny value. It was based on a pretty nominal pit. It's actually pretty big. When I see people's models and they leave the default value, this 0.6865, it sort of says to me, you haven't thought about it. A common number, if I had a 900 by 900 field pit, I might expect a value there of 0.56, and that would be appropriate to a 50% blocked rated inlet. So you definitely need to have a consideration of this particular coefficient. The other option you also have is to actually play with the exponent. You could convert this effectively from the orifice equation to the Weir equation. That is another option. But generally speaking, people will stick with the orifice restrictions in their nodes. So that's one point to note too. In pure 1D models, we also have this inlet capacity option to the top. If I have, I won't spend time going through this particular dialog, but if I had that ticked on, the software doesn't immediately present us with an error, but it is a conflict in our engine. So we can't have this double up of inlet capacity, which is a pure 1D feature, versus the with the 2D inflow. It's sort of a choice of either or.
So you'll get an error.
Yeah, correct. It will flag as an error when we hit solve if I had both of those on. So you definitely need to look for that. The software will try and warn you, of course, at the solve process. I'm going to hit OK there. Just before I move on from this point, I probably also should highlight an important feature of the interface lines themselves. So this polyline can actually be one of two particular formats. It can either be what's referred to as a HX or head-based interface line, or an SX, a flow-based interface line. Again, I believe Chris did talk about these last time, but if I edit the data on this particular line, I'm presented with this dialog box here, and I have the choice between head or flow. And so typically speaking, flow or SX lines are presented at the upstream end of an entity of a system, and SX SX at the upstream and head at the downstream. So that's the general rule of thumb. And if you're after more information on that, again, get in touch with the technical guys here at XP, and they'll be able to point in the right direction of some more documentation on this particular option. But don't forget, simply by right-clicking and editing the data on that particular option is how we get into that dialog box. So that's the general connection between simple gullies and rivers. And again, why might we do this? Again, we're trying to get that relationship between the 1D and the 2D. I'm going to pan all the way to the north on this model and just quickly talk about some boundary-related items that Chris certainly considered in his previous presentation. And I'm going to turn on the active area in this particular model, or I beg your pardon, I'll turn on the grid extents, in fact. And so if this is my model area, this is the grid, again, a 4-meter model in spatial characteristics. We could have had a head boundary across the extent of this particular model, and water would have been lost from the 2D to that particular location. However, I've modified that. I've removed the head boundary from this particular model, and I've applied an additional 1D, 2D interface line across the downstream extent of this particular model, connected it to an external 1D object. So we're basically saying I'm finished with the 2D area. I'm going to pass it back to a 1D object. And the advantage for us in this instance of going down this process is that I get to review the results after running the model. Of course, this model took a couple of minutes to run, so I have already run this particular model. But if I go to the review results button, I'll press F7 inside the software. I get to have a look at the flow relationships, upstream and downstream details, all at this particular location. And in XP tables or in the output files, I can also very quickly have a look at some of the other volumetric characteristics at the outlet of this particular model, rather than relying on the 2D statistics, which do come from the 2D engine itself. So having an additional reporting point at that location, I find is very popular with many users, because we get that this is where the outlet is. I get to see some of those extra characteristics rather than the other alternative, which is a 2D solution, which is to use time series outputs, which we could pepper across the site. And in this particular model, I've only got a couple of those up around the top culvert, but around the driveway, as it were in the previous model. But from these particular graphs, if I right-click on those, so again, time series outputs, I can, beg your pardon, show the flow graphs, and I would get these graphs, but they don't tell me velocity and flow at the same time. So again, that's the advantage of having that single output point to the north of this particular model. I'll just turn those off from this particular model. I'll also turn off that grid. And at this point, I also want to focus in on one last pitfall for 1D, 2D connections, and it is at the outlet from this particular model. If I had the head boundary solution or this external 1D item, if I zoom in around, it's an item that I've seen on a number of models over the last few years here at XP, is what this final node theoretically might do. Even if I didn't have those nodes to the north there, if this was the last node in my model, if I double click in here, I have an option for an outfall. And the outfall option, we can see here, is currently ticked on. And that's a trap. It is a trap because what this does to the model, by having that ticked on, whilst it sounds convenient, I can have free outfalls or fixed backwaters, tidal constraints, all the other boundary conditions, this becomes a black hole in the middle of the model. And so if this was located not so close to the boundary of the 2D model, it could be a relief from the model, and water from the 2D would approach this node and essentially disappear or be removed from the calculations at that location, and therefore wouldn't propagate its way down the river itself if that continued to be modelled in 2D. So we have to be very careful that we don't have 1D nodes with the outfall option selected in the middle of a 2D model. So please, 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 always look for where you have these outfalls located.
So you could use XP tables to pull them all up, see what's ticked on in all of them.
Absolutely. And just to show that process, it's a good comment from Ben. If we go to XP tables, which is either F2 on your keyboard or the spreadsheet icon, if I were to go to, in this particular example, node data, I can add that parameter as a feature. So we go to the setup table variables option, which is the icon to the left of the question mark. And we just have to find that particular flag. And so the outfall flag does reside immediately under the HDR node data in the tree of options. So outfall, and if I append that, it adds it to the bottom of the list. Insert will push it up one above the option below. You can play with that and move them up and down using the arrows on the right-hand side. But if I hit OK here, I can quickly see that I have in this model 2 outfalls, where really, based on my discussion just then, I really should only have one, which would be the final node to the very, very north, external to the 2D area. And in here, in fact, I can actually turn that flag off and rectify the model without even having to go into it. And to prove that, hopefully, if I got the right one, yes, the outfall flag has now been turned off. So very important, please look out for that one. It is one that, again, on support, I would hunt that particular parameter if people have errors near the outlets of their systems. Okay, so that's sort of the really broad overview of those 1D, 2D connections and how they work. And of course, like all good models, when you run the model, we can then review the results of how the flows propagate through the site. And if I turn on the results, it's not playing the game that I wanted to. I did run this one just a moment ago. But we would be able to investigate the relationships between the 1D and 2D options at nodes, for example, which will show me how water gets into the manhole itself. And by not going above the ground, we don't see a ground elevation. So this maximum elevation here is 41.841. And if I go back to the model, in fact, another new feature in 2016, if it was 2016, I can actually drag this particular window to the right. I can hold that data out as I investigate. Now if I hover over that particular node, I can see that on my status bar at the bottom, where I have my X and Y, I also have a Z point because of the DTM inside the interface, and I'm at RL 43.14. So at this point, we're about 1.1 what's that, 1.6 odd metres below the surface with the water elevation at that location. So yeah, don't forget with the new interfaces within the software, you can tree out quite a number of these that work well over multiple monitors too. So
it took quite a long time to do, so enjoy it.
Yeah, enjoy it. Use it. I run 3 screens personally, so stretching these dialogues over multiple screens is quite handy, particularly things like XP tables. Okay, so and of course, again, we do get to if I review the results on links and whatnot, we can see backflow relationships. So water is obviously coming from the creek back into the system for a period of time, and then the system has to wobble its way around to follow the changes in elevations. And these are some very useful 1D results we do get from our models. We can also get into longitudinal data, etc. But that's effectively the overview of 1D and 2D connections in river and urban models. So the key points to look for are making sure we have inactive areas over rivers where appropriate, have those interface lines, either HX or SX types on your models. Make sure your node ponding options on your nodes are set correctly. Please be cautious with that linking the spill crest or the top of the node for gully pits, and the invert of the nodes for rivers, open channels, or head walls, head wall outlets to pipe systems. That's also an appropriate location for an invert connection. Don't have excess outfalls inside your model. Again, you will remove water from your model, and that is quite dangerous. Consider having additional 1D options at the extent of your model for reporting purposes, again, with what can be quite a large 1D, 2D interface line and connection set up to an external carry-on. And the other advantage too here is we do get those additional options with particularly tidal boundaries and the other 1D boundary solutions we can apply inside the XP storm and swim interface. So that's the general wrap-up for me on 1D, 2D interfaces. Finally, Ben, over to you. So training is coming up in those 3 locations, Sydney, Auckland and Perth. So quite a hectic little schedule for the trainers here at XP. But get on board. We do have quite a number of people who have already registered for those. Yep. So definitely get in if you are able to make those. For Australian participants, so for the Sydney and Perth presentations, the trainers at XP will also be talking more about the changes that are happening with Australian rainfall and runoff. So don't miss that opportunity to try and upskill yourself on those big changes to the industry here in Australia, and get in touch with again ausales@xpsolutions.com to get on board. But otherwise, thanks Ben for having me in. Great doing the webinar, and look forward to hearing from you all at another time. Cheers.